Working on electronic circuits comes with a risk of serious injury. This video is for educational purposes only. Please do not attempt to work on any electrical circuits unless you have the required training and experience. Do not attempt repairs yourself. Thank you. Hey guys, a lot of you seem to like last week's video, so I'm going to do a bit more work on this. See, my initial concern when doing these little power supply adapters is that the track is on one side of the board, but the physical component is on the other side of the board. So how do I represent that? Well, what I tried to do last week was just simply replace the through hole component with the symbol for that component and see if we could draw out the circuit that way. And I was happy enough with the way that turned out. So what I'm going to do is I'm going to take it from the bridge rectifier and move on to the next part of the circuit and see if we can build it up circuit by circuit, and at the end of it hopefully have a full explanation of how this works. Last week I found that the bridge rectifier at this position was shorted, and I replaced it with a good bridge rectifier, and then we observed that the monitor came on and that everything was working. But if I didn't have a monitor to test it with, how could I verify that this bridge rectifier is working? The purpose of our bridge rectifier is to convert our mains AC into a high voltage DC, and this is the equation that we can use for calculating this. So our output voltage in DC is equal to our AC voltage multiplied by 1.414 and then minus twice the voltage drop across one of these diodes. So with my multimeter in high voltage AC, I measured across the live and the neutral pins coming in from the mains, and I measured 220 volts. So that 220 volts is our VRMS value. So the other value we need to find out is our VD, which is the voltage drop across one of these diodes in the bridge rectifier. So with our power turned off, we introduce our multimeter in diode mode this time, and we just simply find one of the diodes in that package. We can measure this diode right here. So place my red probe here and my black probe here, and we measured a diode value of 0.54 volts. VRMS is equal to 220 volts, VD is equal to 0.54 volts, so we can drop those values into our equation here, and this is what it looks like. And if you calculate that out, it means that the output DC from our bridge rectifier should be approximately 310 volts DC. So we've established that the output voltage for our bridge rectifier should be approximately 310 volts DC. So where can we measure that? Well, obviously we can measure that on the output of our bridge rectifier right here. So in high voltage DC on my multimeter, just be careful to choose that and not one of the lower voltage DC settings. In high voltage DC, we take the following measurement. We place a black probe to the DC minus output of our bridge rectifier and place our red probe to the positive DC output of our bridge rectifier, and we should measure 310 volts right there. After the bridge rectifier, you'll always find one of these giant electrolytic capacitors like this one right here. The purpose of this is to stabilize that high voltage output DC. So we've got our mains input, which is AC, that's been rectified to DC by our bridge rectifier, and we have this giant capacitor here to help keep that 310 volts DC stable. So to the back of the board once again, I'm going to mark out the paths from the positive DC output from our bridge rectifier, which is this one right here. So let's mark that out. And I'm going to mark out the negative side as well. So this is our DC negative output from our bridge rectifier, so this goes down to here. Let's mark that out. And we can locate the pins of that bulk capacitor, which are here and here. So let's mark in our capacitor. And measuring in high voltage DC at that large capacitor, I also measured 310 volts DC. So what does that tell us? Well, if we have 310 volts DC and a very stable 310 volts DC that's not flickering up and down, it's staying pretty much bang on 310 volts, that tells me that our whole input section here is good. So we've already, if you step out of the circuit, we've already proven maybe a third of the circuit, well, by volume at least, is actually working. So where do we go from here? Okay, so at this point in the circuit, as we've already established, we have a stable 310 volts DC across our main filter capacitor. So what are we going to do with that 310 volts DC? Well, let's see if we can fill out the rest of the little circuit here. So we've got our positive from our bridge rectifier across our main capacitor, and that's coming down here and onto this connection here. If we see that on the other side of the board, we can identify it as the primary coil of a transformer. So that comes across to this position here, and then that connects to the drain pin of a MOSFET. From that MOSFET, the source pin of that MOSFET is connecting then across this track, and at this point between these two there is a current sense resistor. Just to make this easier to understand, I'm going to mark out the pins of that MOSFET as well. So we have gate, drain and source. Now I've confirmed that this is an N-channel MOSFET. So as we've seen many times before on this channel, if you have an N-channel MOSFET, this will be switched on when the gate is high. So let's work out what's controlling the gate. The gate pin is connected along this track right here, underneath this component, across this resistor and onto this pin of U1. So let's mark that out. Now unfortunately I couldn't find a data sheet for this. I'm going to post the numbers that are stamped on top of this IC down below, and maybe one of you guys could help me find a data sheet for it. It might help me do a more fuller explanation of this. However, from experience I do know that this is a pulse width modulation IC. So it's the job of this IC to switch this gate on and off at high frequency, which in turn turns this MOSFET on and off at high frequency. Now because the primary coil of our transformer is connected to the drain pin of this MOSFET, it doesn't have a path to ground, so it is normally not switched on. However, when the gate switches on, that connects our drain to our source and energizes the coil. So with this going on and off at high frequency, that generates a signal that looks something like this. Now this could be a very, very high frequency, but the coil is getting energized, switched on and switched off at very, very high frequency. So that's a brief explanation of what's going on with this circuit. From a troubleshooting point of view, after we've confirmed that we have 310 volts DC across this main filter capacitor, the next thing we really want to know is this MOSFET being switched on and off by our pulse width modulation IC? Now there are a number of ways of verifying that this MOSFET is switching on and off. Probably the best way is if you have an oscilloscope, if you can afford one. If you take a measurement here, you can actually visually see the representation of the waveform on screen. However, not a lot of people have an oscilloscope, so it is possible to measure with a regular multimeter, and I'm going to show you how to do that now. I set my multimeter to HZ, which is for measuring frequency, and very, very carefully I place my black probe to the source pin and my red probe to the gate pin. And when I measured here, I found it measured 41.0 kilohertz. So that means that my gate is being switched on and off at a frequency of 41 kilohertz. And if it's switching on and off at a frequency of 41 kilohertz, then it's obviously working. If it wasn't working, you would probably be measuring zero there, or sometimes it seems to have a tendency to pick up on the mains frequency, which here in Ireland is about 50 hertz, I think. If you're picking up 50 hertz, that means that this oscillation circuit is not working. You're just picking up the frequency of the mains coming into the board. That's where I'm going to leave it for this week, guys. So we've built on what we learned last week about the input section and the bridge rectifier. So I've pushed on into the oscillation circuit, which is just how this MOSFET is switched on and off and how that energizes this primary coil of the transformer here. My goal with this is to hopefully at the end of doing a number of these videos to try and put together one video start to finish that shows how to fully troubleshoot one of these power supplies. So that's the goal, and hopefully that's where I will be in a couple of weeks. I haven't done a few more of these. Please tell me exactly what you think below. Tell me if it works, tell me if it's not working. But the plan is to do the next video on our pulse width modulation IC and then the feedback system. Thanks for watching.